Yeah, once again, a very warm welcome from my side to this online webinar presented by the European Microwave Association. My name is Jan Borowski. I'm with the Institute of Microwave Systems at the University of Bochum in Germany. And I'm very happy to welcome here today Tinette van der Spy, who is giving us an introduction to the Satcube company. And the talk is entitled RF Engineering for Satellite Communications, especially for the low Earth orbit, if I got this correctly. Just to give a few words, Tinette is a Chalmers graduate in the field of wireless photonics and space engineering, and she's pursuing her PhD with Satcube since 2022, researching on the topic of which are the next generation SatCom phased antenna arrays. Yeah, Tinette, I'm very glad to have you here, and I'm looking forward to your talk. If there are any questions, we will have a Q&A panel in the end, and I guess we're all happy then to answer your questions. Okay, the stage is yours.
Thank you very much. Let me just share my screen here. We did practice this just now to make sure everything works, and it still works. Fantastic. So thank you very much for that introduction. As Jan said, my name is Tinette van der Spy, and I'm an antenna and electronic engineer at Satcube, where I'm also finishing or busy working on at least my industrial PhD. And today I want to talk a little bit about RF engineering for satellite communications, but I also want to talk about Satcube, who we are and what we're doing, and a little bit about our vision for the future. Now, I've attended these webinars as a student myself, and I'm very much aware of the very high level of technical knowledge that is usually shared here. For my talk, the focus is maybe a little bit different. I want to focus on conceptually explaining SatCom and the things we focus on as RF engineers, some of the challenges we face, and some of the solutions we have to overcome these challenges. So perhaps instead of focusing very much on theoretical knowledge and equations, instead I want to give an intuitive understanding of what we're doing. So to start off, what I'd like to do is change the slide. There we go. So maybe just a couple of words about Satcube. We're a company based in Sweden, based in Gothenburg, and we were founded as a satellite consultancy back in 2007. But these days we think of ourselves more as a tech company, and we focus on the design and manufacturing of ultra-portable satellite user terminals. And you can see one of these user terminals on the slide here. I'm not sure if you can see my pointer. We've got our headquarters in Gothenburg and a manufacturing facility in Karlstad. And we have 50 employees, so we're still quite a small company, but we are growing very quickly. I do want to just quickly mention that we focus on the ground-based part of the satellite link. We don't actually manufacture the satellites themselves. Sorry, I see there's something in chat. I just want to check that. Oh, we can see the pointer. Thanks very much. I appreciate that. I can also say one or two words about the product we have on the market. It's called the Satcube Ku, and it's called that because it operates in the Ku band, which is between 10 and 15 gigahertz. And whenever I tell my friends about this product, I always say it's just like an ultra-portable Wi-Fi hotspot. So you set it up, point the antenna at a satellite, and in this case, it's a geostationary satellite. And once that's done, it really works like your Wi-Fi modem at home. So you can have Wi-Fi, you can have connected internet if you plug it into the terminal, multiple connections at once, etc. And with our hardware, you can get up to 20 megabits per second up and download speed, depending a little bit, of course, on which satellite provider you use and how much they prioritize your connection. It's a very compact and very portable user terminal. So it's 8 kilograms, and you can throw it in a backpack or in a carry-on case, and everything is rated so that you can easily take it on an airplane and travel. A little bit about the hardware, and I won't go into too much detail, but we have a flat panel array antenna. For this product, it's not a phased array, it's just a fixed beam array antenna. We have a very high power buck or buck-up converter, this 50-watt gallium arsenide solid-state amplifier. For the receive case, we've got a multi-band LNB, and we have everything integrated in this product that you could possibly need to connect to the satellite, including the modem itself. And this modem is connected to which satellite provider you use. And we have several options available. So now that you know a little bit about me and a little bit about Satcube, we can take a step back, and I will attempt to answer the question, why SatCom? Why is satellite communication important? Why is it relevant to the average consumer, and should we be informed? And another question you can ask is, why is satellite communication, has it become so big in the last couple of years? I mean, satellites themselves have been around since the early 60s or 70s, but it's only really in recent years that such a big splash has been made about them in terms of like Starlink or OneWeb or user terminals. So why exactly is that? Well, first we can consider the digital divide, and I think this is a term that most of us are familiar with, but it refers to the fact that there's an inequality between people who have access to quality broadband in their daily lives and people who do not. And the reason for this, or at least one of the reasons, is that the wired infrastructure that you need for good broadband internet is difficult to roll out in certain terrain, such as mountain ranges or rainforests, or if you're in a power station in the middle of the ocean. And I think that's sort of intuitive understanding that we all have. But if we look at the numbers, and this really surprised me when I first started working in SatCom, close to 400 million people did not have cell phone coverage in 2021. 400 million people is close to 5% of the global population did not have cell phone coverage in 2021. If we look a little bit further, another shocking number, 33% of the world population lack access to quality broadband. So this is a section of the population that might have some internet access, but certainly not reliably, and certainly not reliable enough to use in their daily jobs or at work. Furthermore, even if we look at countries such as France and Germany, where we have a high population density and a relatively high level of technological development and infrastructure, we see that 40% of highways have poor to no connectivity. And if we're thinking about autonomous driving, this is simply not something that is going to function. And lastly, even in these highly populated areas with good infrastructure, we need to realize that that infrastructure remains vulnerable to sabotage and natural disasters. About this time last year, I think, there was the big earthquake in Turkey, where a big problem was that the first responders didn't have access to good connectivity and couldn't speak to each other or to the victims. And we also have a similar scenario in the conflicts in Ukraine and Russia and in Gaza, where it's really critical that journalists and first responders can enter the terrain, but still maintain connectivity and get information in and out. At Satcube, we believe that these gaps cannot be filled by traditional wired infrastructure or traditional base stations. But we do believe that satellite communication can step up and play a role here. And we're not the only people to think this. I have here just one quote from a journal paper. The user terminal, and that is now the satellite user terminal, the same kind that we produce, is key in the success of the SatCom network, as it will impact the penetration into the market and will make the network successful and sustainable from an economic point of view. And this is really why I think SatCom has become so relevant in the last couple of years. We've, in the past, had satellite communications in the form of telecommunications or perhaps broadcast TV, but it's the user terminal that's opened up this possibility that we can really have satellite broadband, which we can deliver to the consumer. Okay, so that was just a very brief introduction about me and Satcube and why satellite communications. Now we can dive a little bit more into how do these systems work. And when you talk about SatCom, you need to talk about satellite orbits. You get lots of different kinds of satellites and different constellations, but I've chosen to highlight three, which I think are quite relevant: GEO, MEO, and LEO. So firstly, geostationary satellites, the kind that our product talks to. they're special because their orbit synchronizes with the rotation of the Earth. So if you look at this graphic here, which has a geostationary satellite and a yellow coverage area on the Earth, you can see that that coverage area remains constant. And this is really good news for the ground segment, because it means you can set up your user terminal, point your antenna at the satellite, make connection, and that's it. That user terminal will remain connected indefinitely without needing to scan or steer or anything of that sort. But in the last couple of years, you've also heard a lot more about MEO and LEO. And these types of satellites, as the name suggests, are a lot closer to Earth. However, their orbit is not synchronized with Earth's rotation. So you can see there this yellow line for the satellite in the vertical orbit that suggests its coverage area, and that moves relative to Earth. A lot more complex from a ground segment point of view, because now you need to have a user terminal that can make connection and track your satellite across the sky as it moves. And depending on what satellite you're looking at, this can be from horizon to horizon, anything between 4 and 45 minutes. And then when it disappears on the one horizon, you need to be able to switch to a different satellite and track it without compromising your signal integrity. So I always really like showing this graphic because I think it really gives an idea of scale. And here we've got the geostationary satellites, and you can see they're super far away from Earth, 36,000 kilometers away from Earth. And the reason that they're so far away is they need this distance, or they need to be here to achieve their geostationary orbit. A side effect of them being so far away is that the signal, as it propagates and spreads, by the time it reaches Earth, has a massive coverage area. In fact, you only need 3 geostationary satellites to give you near global coverage. And it's really only near global because of a fundamental limitation. And that's because you can't really use geostationary satellites to give you connection at the North and the South Pole. And from this graphic, I think this is also clear. Even though the signal does kind of reach the poles, if you imagine your user terminal, which you need to put down and make a line of sight connection with the satellite, it's going to be very difficult to point it in a direction where there's no icebergs or mountains or shrubbery that gets in the way of this connection when the satellite, from your point of view, is very close to the horizon. On the other end of the spectrum, we have MEO and LEO, and specifically LEO is very close to Earth, 1,000 kilometers, 36 times closer than geostationary. But because of that, LEO satellites also have a much smaller coverage area. So in contrast to the geostationary satellites, you need thousands of LEO satellites to give you global coverage. However, you can achieve 100% coverage because you can space these satellites in such a way that you can even talk to the poles. And of course, because they're so much closer to the Earth, there are significant advantages in these satellites. Firstly, you need much less power for a signal to reach these satellites. And the time required for the signal to go from Earth to the satellite and back. In other words, your latency is significantly reduced. So LEO satellites have increased performance in terms of latency and data rates. But as we speak now, there isn't yet a company that has a complete LEO network. And here complete means a network that can give you 100% global coverage. Of course, the current LEO companies such as Starlink and OneWeb are working very hard to achieve this, but that's still some years in the future. And there's also a European project called IRIS², where they're looking to build a LEO constellation to compete with these companies as well. I have here a table which summarizes the pros and cons of GEO, MEO, and LEO. I'm not going to go through everything. This is mostly if you want to refer back to this presentation at some point when it's recorded and on YouTube. But in broad strokes, geostationary satellites, their main advantage is this fixed satellite position. However, because they're so far away, you've got very high latency and very high path loss. And on the other end of the spectrum, your LEO satellites, their main disadvantage is the fact that you need to track them as they move across the sky. but they have very significantly improved performance and can offer high performance computing applications such as gaming, trading, etc. I always enjoy showing this picture as well, just to give you an idea of what we at Satcube are working with. So this is coverage from Intelsat and from one of their geostationary satellites. And you can see the dark blue and green shows everywhere that we have coverage. And here we've got checked blue as well. And these areas were set to receive coverage early 2023. So now they are also covered. And you can see the poles are not included, but practically everywhere else is included. And this is a big advantage for us at Satcube because it really means we can ship out one terminal and you can travel to practically anywhere in the world. You don't even have to buy a new SIM card and you can have connectivity for whatever reason you need it. And in our perspective, this is still a major advantage of the geostationary constellation. Okay, so we've spoken a little bit about satellite constellations. Next, we can talk a little bit about SatCom antennas. And I've said here, different strokes for different folks. Each constellation has unique needs in terms of the ground-based antennas that connect to them. And I've said constellation here, but you can really expand that to application. Because even if you're working with a geostationary constellation, for example, where you theoretically have no tracking requirements, if your terminal moves, then of course you once again need to implement some kind of tracking. So if you want to put a terminal on the roof of a car or a plane or a bus, then of course you need to look at some different requirements as well. And speaking about antennas, it's always a very broad field, but I've tried to sort of summarize the three main things we think about when designing antennas for user terminals. The first one is power. So we need to provide enough power to connect to the satellites. And this is, of course, a joint function of our antenna and our front-end circuitry and amplification. Then next is radiation pattern. So we saw from that graphic, if you start off with a very directive beam at your terminal, so a very narrow main beam, that signal will spread the further that it travels. So you need to be very sure that your main beam width, when it reaches your targeted satellite, is not wide enough that it can actually interfere with adjacent satellites. And another thing to consider is if you have side lobes or even grating lobes, these should not interfere with any other satellite or any other communication station, terrestrial communication station as well. And we have some spectrum masks, which I will say a couple of words about in the upcoming slides to help us regulate this. And then lastly, depending on the orbit, or as we've discussed, the application, you might need to have some tracking capabilities to achieve constant connectivity. Then I have this next slide, and I've got the QR code up. Once again, if you want to refer back to this presentation, you can access this tool. And I was a bit hesitant to include this in the presentation because I think for people who are familiar with phased arrays, this might seem a bit elementary. However, if you are familiar with phased arrays, please use this tool when speaking to your friends or colleagues who don't know about phased arrays. And if you haven't heard of phased arrays before, then good news, because this is exactly for you. So if you click here, or if you scan this QR code, it will take you to a link, which I already have open. And when you open up the screen, you will see a single antenna, or at least a representation of an antenna and its radiation pattern. And I know this antenna is an electrically small antenna, and I can know that because the radiation pattern is omnidirectional. So the larger your antenna aperture becomes, the more directive your radiation pattern becomes. So this antenna is horrible for satellite communications. It's a very small antenna, omnidirectional radiation pattern, which means a lot of your energy goes in all different kinds of directions, and probably the energy that you want to go to the satellite doesn't reach it. So what do you do as an engineer when you're handed this kind of antenna? Well, firstly, you say it's horrible for satellite communications, and then you say, okay, but give me 10 more. And then you can make an array out of them. And you might notice that although each individual element has an omnidirectional radiation pattern, if you put them in an array, they interfere with each other. And in some cases, they interfere constructively, and in other cases, destructively. And in this case, you can see this very nice phase front where they all interfere constructively, heading perpendicular from your antenna array. Where in these other directions, you have the energy that's a bit more dissipated. And that's a bit clearer if you click on this contrast option. And once again, we can go to a single antenna. You see energy is radiated out in all directions. But as soon as you increase the number of antennas, the energy radiated in these different angles becomes less, and it all becomes concentrated in this single direction. So effectively, instead of building a larger antenna, you can increase your aperture by having an antenna array. But that's not where the fun ends. This, what you have here, is a standard linear array, not yet a phased array. It becomes a phased array when you ask yourself the question, okay, all of these antennas are excited synchronously, but what happens if we introduce a time shift or a phase difference between adjacent antennas? And that's what this slider here is for. If we change it, now we see there's a time delay between our excitations, and the patterns still interfere constructively and destructively. But this point where they interfere constructively is now at some kind of angle to our antenna array. And this is not new technology. We've known about phased arrays for many, many years, but it has found a really unique application when it comes to satellite communications. Either if you have a LEO constellation that you want to connect to, and you want to track that satellite across the sky, or if you have a user terminal that moves relative to your constellation, then regardless of which constellation you are connecting to. Right, so I hope that gives a little bit of an idea about antennas and power and radiation pattern and phased arrays and how they work. Now, if we come back to our slideshow, just to reiterate, we're thinking about power, radiation pattern, and steering, and we'll talk about each one of these one by one. So firstly, power. I have here a very, very simplified diagram of a user terminal in transmit mode. So your signal starts at your modem, and we get a modulated signal. Us as a user terminal company, we don't touch that signal. That modem comes directly from the satellite providers, and they have their own standards on modulation schemes and which carrier frequencies to use, etc. But that's fed to our buck, our block up converter. And in here, our up conversion happens for up to 10 gigahertz or 10 to 15 gigahertz if we're working in the KU band, or for a different use case up to 30 gigahertz. And also your amplification happens in this block. And then the signal goes to your antenna. There's some antenna gain, and then we send it off to the satellite, and we hope it reaches the satellite. And when we think about power, there's really two things we can focus on. The first one is our antenna size. And as I mentioned earlier, the larger your aperture, the more directive your signal becomes, and the higher your antenna gain. And this is all good and well if you have a user terminal that you perhaps mount on a wall somewhere, where the antenna can be very big. And you can think about these very big parabolic dishes. That's very typical or classical for satellite communication. But if you want to focus on the portability market, like we do, you end up with very strict requirements on antenna size and antenna weight. So if you want to reduce your antenna size, another place you can get your power is in the buck. You can, of course, amplify your signal a lot here and relax the gain requirements in your antenna. However, there are no free lunches, and this also comes with its own set of trade-offs. Once again, if you have some kind of terminal where you have access to a constant power supply, then you really can amplify your signal a lot here. But if you have a portable user terminal, you need to remember that this user terminal is powered off batteries. So you don't have an infinite power supply. And those batteries need to last at least for some time to allow people to effectively connect. And ideally, you'd have a battery that lasts long enough for you to recharge a similar battery. So you can hot swap these batteries and keep your terminal running. Another very big consideration here is thermal performance. Of course, the more power you want to get out of your buck, the hotter it's going to run. And heat is not good for electronics and for circuitry, and you need to think about integrating heat sinks or cooling in this terminal without taking up all the space that you won by making your antenna smaller. So this block here is really where the magic happens in terms of size, weight, and power. And a lot of our consideration goes into how to optimize these for different use cases. To give an example, I have here one of our competitors, the Hughes flyaway solution. And this makes use of a parabolic antenna. It operates in the KKA band, so that means a receive band at around 20 gigahertz and a transmit band at around 30 gigahertz. And it's a low Earth orbit terminal. It has a 1 meter diameter dish. And you can see that's quite a large antenna, electrically large antenna. It's got a gain of 47.6 dBi at 30 gigahertz. That's quite a lot. And then a total output power of 48.2 dB watts. So you can see this terminal doesn't need a lot of power from its buck to actually reach this final output power. On the other hand, we have the Satcube Ku, our flat panel antenna. And you can see the entire terminal in the largest dimension is only 470 millimeters. So a much, much smaller antenna. And that's reflected in the antenna gain, which is only 31 dBi at 14 gigahertz. But we still managed to achieve a final EIRP of 46 dB watt. And the only way this is possible is with our very high power block up converter. And if you're ever in Gothenburg and want to pay our premises a visit, I can show you exactly where this buck is integrated here. And we do actually have a cooling system as well. But once again, all very much focused on making this package small and light. Okay, so we've spoken about power. Next, we can speak a little bit about radiation pattern. And radiation pattern is determined by antenna geometry. And you typically have a main beam and then lots of side lobes. The width of your main beam is directly proportional to your aperture size. And this is very important because it turns out it's this requirement which really determines the minimum size of your antenna array. Or your antenna geometry. It doesn't have to be an array. Earlier, I spoke about making your antenna smaller and trading off the gain that you lose there for more power in your buck. But there's a hard limit. If you make your antenna smaller than a certain value, then this main beam becomes too wide and you end up interfering with networks that you should not interfere with, and your terminal will not be allowed to go to market. So that's what determines the final size of your antenna. And we also need to take into account that whatever antenna geometry you have, it will generate some kind of side lobes, and the level of these side lobes is very strictly regulated. And I can also say here, before I move on, that if you have a single antenna, that geometry determines your radiation patterns, just the geometry of your antenna. But if you have an array antenna, as we have the one here, then two things determine your final radiation pattern. The first is the radiation pattern of your individual element within the antenna array. And the second thing is something called an array factor. And that's determined by the geometry of your array, specifically the shape of the array, and then also the spacing between your elements. That's the array factor. And your final radiation pattern is a product of these two factors. For antenna arrays, and especially when you do scanning, there's another phenomenon we need to take into account, and this is called grating lobes. So I have here on the right a little graphic, and in the graphic, or a little GIF, you've got a main beam here, which is now at 0, and then it scans all the way down to 90 degrees. And you will say when it reaches a certain angle, and I think the angle is about 30 degrees, you have another lobe which appears here. And this is called a grating lobe. And this lobe is exactly the same as your main beam. And its existence is called by something called spatial aliasing. And you can think of this in terms of signal processing and aliasing, where in signal processing, you have a certain sample rate which you need to maintain, and that determines whether your signal will alias around your sampling frequency or not. And it's exactly the same concept for antenna arrays, where you can think about the sampling as your element spacing in your aperture. So you sample that antenna aperture at a rate of your element spacing. And a rule of thumb is if you work with an element spacing of less than a half wavelength, then you can scan to large scan angles without grating lobes appearing. But this, of course, means you've got very strict requirements on the element size that you have to design. So, for example, for the KKA band satellite case, where you've got a transmit frequency at 30 gigahertz, or the highest point of your transmit band is actually at 31 gigahertz, you need to make sure that all your antenna elements are less than half wavelength at 31 gigahertz. And if, for example, you're creating a shared aperture array where a single aperture needs to service both the receive and the transmit band, then those tiny, tiny elements still need to operate and operate fairly well at the receive band around 20 gigahertz. And that can be a significant design challenge. Just to make sure that to clarify, make sure this comes across, you really do not want grating lobes. Not only do they radiate in a direction that's not your desired direction and can interfere with different communication networks, they also steal power from your main beam. They effectively make your pattern less directive, and you see a significant gain drop in your main beam because energy is instead being channeled in this direction. Here I have an example of some of the radiation or spectrum masks that we deal with. So on the left, I've got an example of a 2D radiation pattern and together with a spectrum mask. And on the right, this is a 3D spectrum mask. So here on the left, we see the black line is the radiation mask, and we have an example of a non-compliant pattern where the side lobes are higher than your radiation mask, and a compliant pattern where your side lobes are below the radiation mask. And you will see the mask, it's maybe not so clear from this graphic, but the mask doesn't actually continue here in the main beam. Instead, it's defined from, I can't remember exactly, but something like a couple of degrees, which determine your main beam width. So theoretically, if you had an antenna with infinite radiation in the main beam and no radiation in the side lobes, that would be allowed, as long as you stay within the main beam width. And here's an interesting thing that we do at Satcube. If you work with geostationary satellites, then your radiation mask is only defined in the geostationary plane, because that's where all the satellites are. You don't have any satellites in any other scan angles. So if you have a terminal that remains stationary and is connecting to geostationary satellites, you only have to ensure that your radiation pattern is compliant within that one plane. And that is something that we exploit in our design. So we know the best radiation cut for our antenna is in the largest dimension. So if we have our rectangular antenna, it's in the diagonal. And we've set up our user terminal that you always transmit and receive with the diagonal aligned with the geostationary plane. And we don't worry about the other angles. That's not important, or at least we don't need to get them certified to take our terminal to the market. However, as soon as your terminal starts moving relative to your satellite, so either you're looking at a SatCom on the move use case, or you're looking at other constellations like LEO and MEO, then you need to consider this 3D spectrum mask. So I've just plotted one example here. I think this one was from the FCC, but they're set by bodies like the FCC and the ITU and ETSI. And you need to make sure that your pattern is compliant in all these directions. And you'll notice there's a bit of a dip here as well, if you can see my cursor there. And this dip, once again, corresponds to where the geostationary arc would be. So that you need to keep track of that the whole time, whether your terminal is moving or your terminal is stationary and the satellite moves. You need to know that there are stricter requirements in the geostationary plane than there are for the rest of the scan angles. Okay, so we've spoken about power, we've spoken about radiation pattern, and the last thing we're going to speak about is electronic or is scanning. And there's a couple of options when it comes to scanning. The first one is electronic in the form of phased arrays, and we've already seen how this operates from the previous antenna tool that I shared. One big advantage of this is it's compact and transportable. So if you want to have an antenna that's in a funny shape, or you have a funny shape constraint, you can always have your phased array and individually control your elements to take into account the shape of your array and create your radiation pattern based on that. But as I also mentioned, there's very strict constraints on individual element size and spacing. And another very big problem is that for this to work, each antenna needs to be individually controlled. So you have these chips which control the amplitude and phase of each antenna element. And while those chips, we call them beamforming chips, are individually not very power hungry, if you have a system with 1,000 elements, which is typically the kind of system that we're looking at, they end up being very power hungry. So with a typical 1,000 elements array using around 50 watts. And that's one consideration. The other consideration is, once again, the thermal performance. So it's very easy to forget when you're just looking at the one tiny chip. It doesn't seem to heat up that much. But if you've got many of these chips in very tight integration, they very quickly heat up to the point where your phased array will simply stop working. And that's a very challenging design constraint to work under. Then I can also mention a couple of words about scan loss. So scan loss is a fundamental limitation of electronic scanning. And this is because if you have a broadside beam, broadside is when there's no scanning, your antenna beam is simply perpendicular to your antenna array. If you look from that scan direction, from broadside, you see the entire antenna aperture. And that entire antenna aperture is effective for antenna gain. However, when your beam starts scanning to, say, 60 degrees, then you need to imagine yourself looking at that aperture from a 60-degree angle. And now what the aperture area that you see seems to be decreased. And we call this the effective aperture, which is the projection of your aperture in the direction that your beam is pointed at. And this is at a maximum for broadside and reduces the further you scan. And with a reduced aperture, as we spoke earlier, you've got less antenna gain. So we see this gain drop here in this picture. The further you scan, the less directivity you have, and your main beam widens. So when you're designing one of these systems, you need to know what your maximum scan angle is going to be, and you need to design at this design point to make sure your main beam width is regulatory compliant and that you have enough power to reach the satellite in question. And this is another very challenging design constraint to work with. So if you decide, oh, electronic scanning is too difficult, too many things to think about, another option is mechanical scanning. And I feel like this is a very intuitive reaction when you first tell people, oh, I need to track a satellite across the sky. They imagine some kind of antenna on a motor. And like I say here, your antenna beam stays constant with regards to your antenna, but you move the entire structure. However, these solutions, while they seem initially simpler than electronic scanning, you do have to have quite complicated motor control to get them to work correctly. Some systems can work with 2-axis control, but very often 3-axis control is necessary if you want very good tolerances and very good control. And the requirements on the motors used here is very, very strict. Obviously, a very small pointing error of your antenna can result in your main beam completely missing your satellite. So that's a thing to consider. And the big challenge is if your satellite that you're tracking disappears across the horizon, you need to very quickly switch to another satellite. So that's could potentially be quite a heavy geometry of your antenna, moving very quickly and coming to a very quick stop, a very precise stop, without shaking the system too much. That's quite challenging to manage. So at SatCube, we've looked at both of these options. We've looked at electronic scanning and at mechanical scanning. and we see advantages and disadvantages to both. However, for a portable user terminal, we would probably disregard this mechanical scanning because it's large and bulky. There's lots of moving parts. They're prone to mechanical wear and tear. I say that, but of course there are also some products we're looking at which have mechanical steering for portable user terminals, but they are very challenging to design. And then lastly, we come to something called hybrid scanning. So the idea here is that you combine your electronic and your mechanical scanning in some form or another. And there's a couple of different ways to do this. And one which seems very promising is that you have electronic scanning in the one dimension and mechanical scanning in the other dimension. So for example, I have here a paper where they've done something like this, where you have, in this case, one array for your transmit frequency and one array for your receive frequency. And you can see the receive array has a lot larger aperture than the transmit array because the receive frequency is a lot lower than the transmit frequency. So electronically, the aperture size is actually quite similar. And this array has scanning in the one direction. And you can see they've actually tilted the individual array tiles so that your broadside is not at zenith, but it's slightly offset. And this is a big advantage because then it means you only need to scan to plus minus 40 degrees to cover practically from the horizon to zenith. And that's the one direction that electronic scanning works in. And then your mechanical scanning comes in at this rotating base. So you can scan up and down vertically with electronic scanning, and then the base rotates to make sure that you can reach all possible scan angles. And this is a nice solution. A lot of people have thought about this, but there are also some challenges here. The main challenge that we came across when looking at this is you, of course, need cables that go from your array to the rest of your terminal circuitry. And those cables need to go around your rotating base. And if you, as would be the theoretically ideal case, have a base that can turn indefinitely in the anti-clockwise direction, and then again indefinitely in the clockwise direction, these cables will just rotate around the base until they break. So practically you have a hard stop. You can only rotate so far in any direction. And this then leads to the scan case where you will be continuously tracking a satellite and rotating, and then you reach the maximum of your mechanical rotation, but you need to scan further. So what then has to happen is the turntable has to rotate very quickly 360 degrees and then compensate for the electronic steering. And this leads us right back to the same problem we had with the mechanical steering, that we need very, very good motor control. We need to be able to move potentially large and heavy antenna very quickly and very accurately and come to a very quick stop. Another solution, if you want to avoid these cables, is to have some kind of rotating joint or connections. And that's also something we've looked into and seems to be a very good and nice solution. But it adds complexity and is another step in the design process. But I think if you were to design such a system, that would be the way to go. Next, we've spoken about satellite constellations, about SatCom antennas and user terminals and the things we think about when we design them. I want to have the last section here, Satcube and 6G, which shares a little bit about our vision for the future and how we understand the role of satellite communications in the new generation of the communication network. What I have here is a very generic picture. I think if you look at any journal or conference articles about 5G or beyond 5G and 6G, you will find some variant of this picture, but it basically shows a very nice overview of what the communication system could look like. And at the moment, satellite communications is here. And this picture is meant to represent remote areas with maybe low population density or remote areas where it's very difficult to have wired infrastructure, like the middle of the ocean. But then Starlink came and they made their big splash with their low Earth orbit satellites. And the people who had been planning 5G had not expected this. And a lot of new legislation had to come out about how is satellite communication going to fit into this network. You know, how are we going to share the spectrum? All these kinds of things, and a lot of reactive legislation came about. But before I get too much into that, I see I have two use cases for the Satcube, our product, where it works in these kind of scenarios, so very remote or far away places. And the first one here, I can't actually remember this guy's name. I think it's Richard Geisen, but this is from 2022. And he actually finds himself in the Ukraine. He was a journalist, and he was covering the emerging conflict between Ukraine and Russia. And this photo that's shown here is a still of a interview that he did on BBC Today, I think it was. And he did this entire interview purely using the Satcube Ku, and this was shortly after an attack from Russia. So this is something where we often see our terminal being used in some kind of remote scenario where you have no access to terrestrial communication networks. And although we often see the terminal being used in, if I can say, unpleasant scenarios, disaster scenarios, we also have a couple of happy user examples. So this here was taken from a project of called Coffee with Turtles. If I remember correctly, this was a project that happened last year where a group of nature conservationists and journalists took a Satcube terminal down to the Amazon rainforest and covered the Amazon River turtle nesting event. And it was a live stream that was running, and you could dial in every time and have coffee with turtles as you watch them. I think the link is still available on our LinkedIn page if anyone is interested in taking a look at that. So that's sort of the traditional use of satellite communications. However, for 6G, we hope that we can take a clean slate approach, and instead of being reactive, be proactive and plan how satellite communication can fit into this network from the start. And some markets where we see potential, I've highlighted here the plane and the car. And the airplane is I highlighted here, but it's actually something that is happening and has happened for quite some time, where you have satellite terminals on the top of your airplane, and they facilitate people who are streaming while they're flying, or messaging, or joining Teams, online meetings, etc., etc. And this is something that has been well established and works really, really well. On the other hand, we have this massive untapped market called SatCom on the move. And this picture here is of a car, but really it should represent trains, cars, potentially tractors, because we're speaking a lot about autonomous agriculture. And this can either be for cases where you have autonomous driving and you need some kind of connectivity on your car, or for cases such as buses and trains where you have a very high concentration of people who demand a high quality broadband internet connection. And then we also see definitely a use case for people who want user terminals who already have access to terrestrial broadband connections. And the target market here would probably be banks or hospitals who want some kind of secure connection that they can know will remain connected regardless of potential disaster. And that brings me to the end of my talk. I want to thank everybody who sat through my talk. I hope it was engaging and clear. If you want to know more about Satcube, please send us an email, send me an email. I have my contact details on the screen, or find us on LinkedIn. We're always very responsive. And perhaps I can now hand over to Jan, and we can see if there are any questions that I can try and answer.
Yeah. Thank you, Tinette, for this very, very interesting talk, and very nice introduction to the whole topic. Yeah, to all people in the audience, there is this Q&A button that you could see in the bottom of your Zoom window, or you can use the chat window as well to ask your questions. And yeah, I will forward them to Tinette, and I guess she will be happy to answer your questions. And I think there is
right. I've opened the Q&A box on my screen. I don't know if that's visible to everybody or just to me.
Up to now, it's only for you, I guess.
Right. So Maybe I can just read out this one question and answer. So we've got a question: is the Satcube terminal using a shared aperture at Ka band? So currently our product works, the one that we're selling, works at the Ku band, and yes, that one is shared aperture. We're investigating options for the KKA band, and there are different directions in which that investigation is going. And if you want to know a bit more about that, then send me an email and I can share some more details. But yeah, we're definitely looking at shared aperture. The challenge is always just, if you have shared aperture, you run into that problem where you have these very tiny elements to facilitate your scanning at TX frequency, so half wavelength at 30 gigahertz, but your receive band is at 20 gigahertz. So that means effectively your gain in the receive band is very severely reduced, and that might mean you have to increase your entire aperture to fulfill your power needs. And so effectively, if you have a shared aperture with a fixed area, but you have a 3 dB loss in gain, that's pretty much the same as having a dual aperture for double the area. So this is something that we keep in mind, and yeah, different strokes for different folks. It depends on exactly what application you're looking at. Sometimes it can be an advantage, sometimes it is a disadvantage.
Yeah, maybe while we wait for further questions, I have one myself. Oh, okay, now that keeps us up for later. Maybe,
Right.
Tina, do you want to read that?
How resilient is your product to jammers? That is a very, very good question. And this is not my area of expertise, but I do know we have two variants of our product. The one is the Satcube Ku, and this one is Satcube Ku Secure. And our product is very often used in critical scenarios. And for that one, we more often sell the Satcube Ku Secure, which is supposed to be very resilient against jammers. I can't really quantify that for you because this is not really my area of expertise, but a very good question. Thank you for that. Right. And we have another question. If I heard it correctly, you're not using a phased array for the Ku band terminal. If not, how do you focus a beam? Right, so the Ku band terminal is not working with LEO satellites, it's working with geostationary satellites. So we have an array antenna, but not a phased array, because everything has got a fixed amplitude and phase, all the individual elements. So you cannot scan that beam. But because of the aperture area and the way in which it is designed, this array antenna still focuses the beam in a specific direction, and this direction is broadside in this case. But I say it's not a phased array because we don't have the opportunity to change the phase and amplitude of our individual antenna elements. I hope that is clear.
Yeah, maybe then I have one myself. You showed us very nicely, Tina, that the gain of your phased array decreases as you increase the scan angle, of course, because the projection of the array becomes smaller. So what is in your design point? Is it the maximum scan angle, or and you're happy for the additional gain at broadside, or how is it computed?
That's a very good question and a very big headache for designers. So yes, this is you have to look at the maximum scan angle, and that determines some dimensions, like your aperture area, for example. But you need to consider simultaneously your antenna at scan and at broadside, because sometimes you can design an array to have a very good reflection coefficient for 60 degrees angle scanning, and then if you check the performance at broadside, it's completely destroyed. So yes, you need to definitely, one design point is at the maximum scan angle, but you need to simultaneously optimize for that maximum scan angle up to broadside. And you can pick a couple of critical points and simultaneously optimize for them.
Mm-hmm. And the additional SNR that you have at broadside, is it used somehow in the modulation scheme so that the link switches to higher order modulations or something like that?
That is something that happens on the satellite operator side, and yes, definitely. You do get higher performance if you have additional SNR. Something to keep in mind, however, is that you're very seldom, when you're scanning, you're very seldom at broadside. you're more often in this sort of 10 to 40 degrees scan angle range. So there are some designs where indeed you can push up your performance at these scan angles, and that results in some degradation of your performance at broadside, but that's actually more advantageous for the entire system. Yeah.
Okay. Yeah. Yeah, there is another question.
We've got a question: how close can two terminals be kept on ground and still work? They can be very, very close. You can have them practically touching. So our two terminals, or our terminals, they're very directive beams, and they have, unless you're pointing them at each other, they have very little risk of interfering with each other. How do you deal with antenna coupling and active reflection coefficient when scanning a beam? Wow, that really cuts to the heart of the issue. Very good question. So I can speak a little bit about my work as a PhD student, because this is very much focused on antenna coupling and active reflection coefficient. And the best answer I can give is you have to approach it from many different directions. So there are some hardware designs where you can design your array and your antenna element to reduce antenna coupling. And for those of you who are not aware, antenna coupling is if you excite one element in your array, it's going to, of course, radiate some of its power to the adjacent elements, who will once again radiate back. And this makes the design of your array very challenging. It's something you have to take into account. So on the one hand, you can go from the hardware point of view, and there's lots of research that has been done on how to reduce mutual coupling. You can also design your hardware if you're using an EM solver like CST. You design it in an infinite array environment, and that gives you a very good idea of what your active reflection coefficient could look like. So you don't design your element for a normal reflection coefficient, but for an active reflection coefficient, which means it's the element considered in an array where all elements are excited at the same time for different scan angles. On the other hand, and some very interesting work we've done last year, is you can use certain optimization schemes and certain software to actually exploit this phenomenon of mutual coupling to give you more gain in your array. And you do this by taking your entire array into account and optimizing for the total active reflection coefficient of your array. And that effectively gives you a nice beamformer distribution, so how you excite the individual elements in terms of amplitude and phase, which actually improves your reflection coefficient. But yes, I've done a lot of work on that specifically, so I have perhaps a lot of information to share, and if you're interested in hearing more about it, please send me an email.
Yeah, maybe while we wait for another question, another one from my side. How is the tracking done? Is it completely RF link power based, or is there external information available, like the trajectories of the satellite that you want to track? So in principle, you could have something like this from your provider.
Exactly, and you've hit the nail on the head. It determines it depends very much on your satellite provider. So I know a lot of the development work that we're doing is based purely on external information, so satellite trajectories, and we have, of course, in our terminals and also in the future terminals we're developing very precise GPS and gyros and all these things to measure exactly the position and orientation of your terminal, and then based on that to connect to the satellite. And this works surprisingly well. When I first heard that this is how it was done, I was quite surprised, because I thought satellite is a very, very tiny speck over the entire skyscape, but you can actually manage to establish a connection quite well in this way. But then, of course, there are some other opportunities where you measure your signal strength and adjust based on that, of course. Yeah.
Yeah, there is another question, I guess. It's about the networks that you can.
Oh, what are all the networks that the Satcube terminal can talk to? Oh, good question. We do have a list of satellite providers. I don't have that list off the top of my head. I know one of the ones we use very frequently is Intelsat, and the reason for that is, like I showed earlier, it's got this very nice global coverage. It's certified to work in many different countries, so you don't have to go through different regulations for each country you go to. If you send me an email, I can send you a list of all the operators we work with, but I should highlight that this very much depends on which modem is integrated in your terminal. So satellite providers will only speak to terminals with their specific modem. So if you buy one or if you rent a terminal, you rent an Intelsat terminal or a Viasat terminal, and you can only speak to those satellite providers one at a time. Although we are considering and investigating the possibility of having a so-called universal modem. But of course, this will not only have to be a development from our side, but also from the satellite provider side.
Yeah, maybe at some time in the future. So I remember cell phone networks operating at different bands, and when you travel around countries, you used to have different phones 20 years ago or something like that.
Exactly, that's exactly the same scenario, and we've got hopes that with 6G and looking at satellite communications as a really an integral part of the communication networks, that there are maybe different standards or regulations that will arise to help standardize everything and make it a bit more uniform. But we'll have to see how it develops.
Yeah, because you mentioned 6G and the ongoing mobile network developments. Do you see any movement in the frequency ranges that are of interest for satellite communications, or will it be, or is it supposed to be fixed at Ku, Ka band, these regions?
That's a very good question. I'm hesitant to give a definite answer on that. I can just share my opinion, and I think it would be very expensive to change the frequency ranges at this point, especially when considering the satellites themselves and the number of satellites that have been launched. So from that point of view, I would be surprised if the frequency ranges change significantly. But this is really not my area of expertise, so I can't really give a definite answer.
I don't want to overstress it, but I have a last question maybe. So you mentioned at one point you have these beamformer chips behind your antenna that can steer the magnitude and phase of the signal. So we mostly talk about phase when steering the beam, but of course you can do an amplitude tapering as well to achieve a window function. Is this done, or is it too costly because you can only lower your amplitude, to be honest, right? So you throw something away, you lower your maximum gain. Is this affordable in your application?
Absolutely. In fact, it's a necessity because we have these very strict spectrum masks, and that's maybe something that will change in the future. But currently, these radiation masks, they were defined back in the day when people assumed that the only kinds of antennas that would be used in satellite communication on the ground would be big parabolic dishes. So for a parabolic dish, it's very achievable to meet these masks, but for an antenna array, where you perhaps have higher side load levels, it's really very, very difficult. And in many cases, we believe the masks are over-specified. It was simply a relic of how things used to be done. So that's something that we hope will change, because I think we can get a lot more performance for very little cost if it does change. But yes, tapering absolutely does take place. And very interestingly, if you have an array and you've got uniform amplitude, that is going to result in giving you the highest power, but it's not, or output power of your antenna array, but it's not going to give you the highest efficiency. If you want to get the highest efficiency, you need the optimal total active reflection coefficient. And that almost always comes with amplitude tapering as well. And when you're thinking about terms of energy efficiency and thermal performance, this is crucial. I see there's one more question. Do these support single beam or more at the same time? So our current product, the Satcube Ku, only has a single beam. It's a fixed array antenna with a beam at broadside. But if you have a phased array, you can of course have more than one beam. You have complete control within certain limitations of your the shape of your radiation pattern. So there's something called make before break, and this refers to the fact that if you track an antenna that's about to disappear behind the horizon, you split your radiation efficiency in two and create a different beam to point at the next antenna that you will track. So you make that connection before you break with the original antenna or satellite, but then you also get break before make, which requires just a single beam. But as soon as the satellite disappears, you have instantaneous beam switching to the next satellite. And there's been studies done on this, many studies. I'm thinking currently of one done by Viasat, where they found that this break before make architecture, where you only have one single beam, is more than sufficient to maintain your signal integrity. So yes, you can have more than a single beam, but it's probably not necessary.
So, if there are no further questions, I'd like to thank you. Oh, okay, that's just feedback. Appreciate it, I guess.
Thank you.
Yeah, Janet, thank you very much for this very interesting talk and the very nice discussion afterwards. So I'd also like to thank all of you in the audience for joining us here, and yeah, stay tuned for our next webinar. Thank you. Bye-bye.
Thank you very much.